This is the second set of notes, PowerPoint B, for Chapter 15 on energy and chemical reactions. We're going to talk today first about Section 2 and about calorimetry. This is a calorimeter. Yes, we spare no expense here at Canyon High School. Actually, this is a pretty fancy one compared to our normal white cups. So this is basically a styrofoam cup with 100 milliliters of water, which is 100 grams. You should know that 100 milliliters of water is 100 grams because for the lab, we're going to measure 100 milliliters in, then it asks what's the mass. So you should know that. Basically, thermometer, we also have a lid on top, something you need to be very careful about when you do your lab. Don't let the thermometer touch the lead when you put it in the hot lead because that will be 100 degrees, and that'll be about a 400% error. We're measuring the temperature of the water, so it's got to be above. If you can't figure out how high to put that, then basically just put the thermometer in and measure the water up above and watch it. One way you could do that is to kind of figure out by lining it up on the outside how far it needs to be, and then tape this to where it's up in the water. So that's your calorimeter. The equation that we're going to use for calorimetry, whenever you see calorimeter or you see that you have the temperature change in temperature, of course you know you're going to use Q equals MC delta T, but it's a special case here because the heat gained by the water is equal to the heat lost by the object. So Q of water equals Q of object. That means we're going to have MC delta T of water equals MC delta T for the object. And that's the way you should start your calorimetry problem, is by setting two sets of MC delta T's equal to each other. The little W equals for water, O for object on this one, and we're solving in most cases for the specific heat, which is the letter C of the object. So the other method here, since they're equal, you could solve for the heat of the water and then plug that into the Q up here. That's actually just be Q, not delta Q up on the top. If you plug the heat of the water in for the heat of the object and then the mass and delta T of the object, you're solving for the specific heat of the object. So really two approaches there, two ways we could do that. This is chapters about thermochemistry, so we're going to kind of define all that. Thermochemistry is study of heat changes that accompany reactions, both chemical and physical. We have to define the system and surroundings because we're going to talk about heat being gained and heat being lost. What does heat being gained mean? Well, it means that we put heat from the surroundings into the system. The system is going to be the container that holds our reaction. The surroundings are the outside, the system's the inside. The surroundings, they go infinitely out. So when you add the systems plus the surroundings, that equals the universe. So the universe is like the whole thing, everything. Enthalpy is the energy that's contained in the system, and we're going to calculate the changes in enthalpy. But we use the symbol H for enthalpy and delta H for changes in enthalpy. This equation down at the bottom, delta H of reaction equals the delta H of products minus delta H of reactants. We're going to use that 3 or 4 places. And there's a chart in the back of your book, R11. It's page like 990, 997, way in the back, chart R11. I made copies of that in class that you'll get for possibly useful page where you actually look up the heats when you do heat of formation. We'll talk about that a little later. Thermochemical equations. It is what it says. It is a chemical equation that also has thermal information. So what you're looking for the thermal information is something in addition to what we've talked about before with chemical equations. It'll be a plus and then some number in kilojoules, or plus and some number in joules, or plus some number in calories or kilocalories. One of those 4. That would be the thermal information that makes it a thermochemical equation. On the quiz and test, I'm going to give you some of these and say, is this endo or exothermic? How do we determine that? Well, if you look at the first equation, notice that the 1625 kilojoules is on the right as a product. that means it's given off as a product out of the reaction. If it exits, it's exothermic. There's another way we could state that if I don't give you the 1625 as part of the reaction, but it tells you heat of reaction is negative 1625 kilojoules, like over underneath the equation on the left, then that also means it's exothermic. A negative delta H is exo. So the next equation has 21 kilojoules as its first item. It's on the reactant side. We're adding it. When you add or put in, then we think endothermic for put in, endothermic. And again, if it doesn't have that factor, that 21 kilojoules in the equation, but it has it below or beside it, it says delta H of reaction is positive 21, that positive means we're adding. So be able to identify endo and exothermic by either of those two methods. For enthalpy calculations, there's several different enthalpy calculations, but one of these involves the letter Q again, and it's going to be Q that is used with an H factor. Now I do this a little differently because there's like 8 different H factors, and you really could use the same equation for that. In general, most of the calculations we do are going to be state changes, and there's an H factor for each type of state change. We call these heat of molar heat of condensation, molar heat of vaporization, molar heat of combustion, molar heat of fusion, molar heat of solidification. For short, a lot of times we'll just say heat of vaporization or heat of condensation. And that's probably better because sometimes we don't deal with a mole. In the labs, we don't use mole, we use grams. So I've given you both of the factors, the conversion factors, the H factor that goes here, and the M can either stand for mass or moles depending on what your problem needs. So it can be mass times the H factor in terms of grams, or moles times the H factor in terms of moles. Both of those are on the next page for water. And if it's something other than water that I give you in a problem, then you just look it up on a chart in your book, and they have the H factors, or the heat of condensation, heat of vaporization, for the other substances. You should know what these words mean, like heat of combustion, heat of vaporization. Look over them. Notice I have 1 star, which means that it's endothermic by heat of vaporization and heat of fusion. I have 2 stars, meaning it's exothermic for heat of combustion, heat of condensation, heat of solidification. In other words, heat comes out for those. So you should know which ones are endo and exothermic. Just look at the stars. Here are the values for water, and notice that heat of vaporization and heat of condensation have the same numeric value, although when we're losing the heat, it's a negative value. When we're gaining, it's positive. So just keep that in mind. When you're doing calculations, you're using the same value. And then you just think of the symbol or sign based upon is heat coming in or is heat going out. So heat of vaporization, heat of condensation for a mole is 40.7 kilojoules per mole. For water, 1 mole weighs 18 grams. So if you divide 40.7 by 18, you get the second factor, which is 2.26 kilojoules per gram. Now notice that's kilojoules. There are some other factors that deal with joules. We always have to have kilojoules and kilojoules when we add them, or joules and joules. The second number, heat of fusion, equals the heat of solidification. Remember, one of them is negative when you're losing. And that value is 6.01 kilojoules per mole. Easy way to remember this is the low one is the ice and water, water to ice. The high one is the steam to water, water to steam. So there's more energy in the steam. So you remember the big number is the hot steam. And if we divide 6.01 kilojoules per mole, we divide that by 18 grams instead of mole, you get 0.334 kilojoules per gram, which is 0.334 kilojoules per gram, which is our gram factor, or our gram number that we use for the H value. Page 530 has a chart with other substances if you're given something besides water. I will give you that chart. I'll also give you these factors. Anytime we have a state change, there's no temperature change, so if you're asked to solve for the heat of a state change, it will be Q equals mH. If you're asked to solve for the heat of a temperature change part, like we're going from 0 to 100 degrees between state changes, then it's Q equals mc delta T. And so calculating enthalpy changes, again, that's what this sums up. It says if it's temperature change, Q equals mc delta T. If it's state change, Q equals mH. Hess's law is the next thing that we're going to look at. It says down on the bottom that it basically tells you that if there's more than one reaction that makes up an overall bigger reaction, then you add up the heats of the small reactions to get the total heat in the big reaction. And that's kind of like going to Walmart. You go to the checkout, you got 3 items, they total it up and give you one total for all the items. So it's kind of like checking out at Walmart. So applying Hess's law, we're going to look at this top section, and this is something I've put in that really the last book didn't include, but it is something that you cover in AP. In AP chemistry, when I've taught it, I cover this, and probably if I put this in on a test, it might be a bonus question, but it's worth looking at. And what we do on these problems, you'll be given a reaction, and the reaction is a big reaction. It's like an overall reaction that's made up of 2 or more subreactions. And what Hess's law says is that the subreactions add up to the total of the big reaction. Well, they'll ask you how much enthalpy total is in this reaction. What you have to do is look at your chart, one of the charts from the back of the book, for the reactions that make it up, the little subreactions, and add those up. Now, there's a couple of tricks. Sometimes you have to double a reaction or triple it to make it fit your case. Sometimes we have to take the reaction on the chart and flip it. And if you do that, you have to make the sign negative for the value. If it was negative, then you turn it positive, because a minus of a minus is a plus. So that's what I've got summed up. This is actually a page from your chapter, and you know, to get this better, probably best to kind of follow through and see what they're doing step by step. It's straight out of the textbook. Notice that they have flipped the second reaction so that our product is SO3, because the way that it's listed on the chart is SO3 as a reactant. So we turn it, and now SO3 is a product. And the things produced by the first reaction fit right in with the second reaction, and it all works. Now, the only problem is the first reaction, we've got 1 SO2. We need 2 in order to fire up the second reaction. So for the second reaction, since we need 2, just put a 2 coefficient in front of the first reaction all the way across. And when you do that, you'll have your reactions to where they mesh together. Flip the second one, put a negative sign on it, and notice that when you sum them up, you add them all up, and there's SO2, 2 SO2 produced by the first one, used by the second one. That's kind of like if you make 2 batches of cookies and 2 dozen and you eat 1 dozen, well, then you're not going to have that dozen, so you produce it and use it, it gets crossed through. That's why they cross through the 2 SO2. Total reactions up, everything on the left ends up on the left, everything on the right ends up on the right. Notice at the bottom they sum all that up. They also add up the total delta H, and that gives you the delta H for the overall reaction. The other problem, it is a 3-step problem that you have to do. Calculate the heat resulting from melting 10 grams of ice. Use MH. Calculate Q for melting. And then you calculate the heating from 0 to 100, which is Q equals MC delta T. And then you've got one more state change where you have to use the heat of vaporization. Solutions on the next page. Make sure you know how to do 2 and 3 steps problems. You'll have at least one of those on the test. The standard heats of formation, that's the next thing. And Basically, you're using the delta H equals the products minus reactants. There's a chart that I've handed out in class that's R11. Look it up. You look up your products and your reactants, and we use our summation equation, that last equation on the last page. So you sum up, balance the equation first, sum up all the products, minus the sum of all the reactants, and you subtract that and you get overall delta H, and again you get those values from R11. There's some example problems, try some of those, and that is it for the notes PowerPoint B. Good luck.